Hello there, Mr. Sutton here, bringing you the AB Calculus 3.4 homework solutions on graphing derivatives. For number 1, sketching the graph of this derivative, easiest thing to pick out is where the slope is 0, so that would give us an x-intercept for the derivative. And then to the left of that x-intercept, the slope is positive, so we know the derivative has got to be above the x-axis for that spot. Over here, our slope is negative, or it's decreasing. So we know our derivative is going to be below the x-axis. So starting above, ending up below, looks something like this. For sketching the derivative on number 2, we'll start by picking out the places where the slope is 0. So right about here, we have a slope of 0. And here as well, at this smooth turnaround. Now let's see where the derivative is positive and negative. We're going down here on the original, so we have a negative derivative between these. And then here we've got a positive derivative. So we're starting below the x-axis for our derivative, hitting this x-intercept, and then we have to come back down because it's still negative, and then we go through on that last one. On number 3, let's graph the derivative. We'll start this by picking out the places where the derivative is 0. So we have an x-intercept for the derivative right here at this smooth turnaround, and also for this smooth turnaround here. To the left of the first x-intercept, we have a negative derivative. Then we're going up on the original function, so that's a positive derivative. Then we're going back to a negative derivative. So we're starting below the x-axis, pretty close to 0. And then we have to go through this into positive territory, and then come back down into negative territory. And you'll notice this slope is kind of tapering off, so our slope should be approaching 0 again as we move to the right. To graph this derivative, let's put x-intercepts for the derivative wherever the smooth turnarounds are here. So here's an x-intercept, here's another slope of 0. To the left of this one, we're decreasing on the function, so the derivative is negative. In between these x-intercepts, our derivative is positive because we're going up on the function. And going back down on the original, that means we have a negative derivative there. So we're starting negative, going into positive land, and coming back down into negative land. For the derivative on this one, we have a smooth turnaround, so we have an x-intercept here, and another smooth turnaround gives us an x-intercept here. We're starting positive for the derivative because the original is going up, then down, so negative derivative, then positive derivative over here because we're increasing on the original. So we're starting above the x-axis for the derivative, coming through this x-intercept, going into negative land, and coming back up through this other x-intercept for our derivative graph. To graph the derivative on number 6, let's first pick out the places where the slope is 0. There's really only one on here. It's this spot right here. So we have a smooth turnaround, which gives us an x-intercept for the derivative right there. Before that, we have a positive derivative because our original is going up. And then we have a negative derivative. However, this negative doesn't keep getting more negative. Notice that our slope is getting closer and closer to 0. So to graph this, we have to start in positive land, come through the x-intercept, and then we're going to have to come down but then approach that x-axis again to show that our slope is getting pretty close to 0. For number 7, we need to graph the derivative of this thing. Let's start by identifying some discontinuities. This vertical asymptote here on the original will give us a vertical asymptote on the derivative. Same thing over here at 2. They actually labeled the grid lines here. Let's also pick out the places where the derivative is 0. So we have a smooth turnaround right here, and here at 1. And now let's figure out where the derivative is positive or negative. So we're starting off in here in this little interval negative, then we become positive, then negative again because we're going down, and then positive as the function increases. Next, let's graph it. We have to start in negative territory, approaching this asymptote. So we're going up through this intercept, and then positive land, back down through this intercept, back up through this intercept, and we're going to approach the asymptote and just keep going higher and higher there. So something like this might be one possible graph for this. For number 8, we're trying to graph the derivative of this function. So notice that we have this cusp here. A cusp means we have an undefined derivative, so we're going to do an asymptote right there, because we're getting infinitely steep from either direction. And we also have a smooth turnaround over in this area, So that'll give us an x-intercept for our derivative about there. Now before this asymptote, our derivative is going to be positive because the function's increasing. After that asymptote, now our derivative becomes negative, and then back to positive after that smooth turnaround. So let's try to graph this thing. So we're starting above the x-axis, and notice that as we move further to the left here, it's kind of tapering off close to 0 for the slope. So we'll start our derivative graph also close to 0, and we'll follow this asymptote up, like so. Now for this one, we're decreasing, and we have to go through this x-intercept. That tells us that we need to start, let's see, down here, because our derivative is negative. So we're going to be approaching this asymptote like so, going up through this x-intercept, and then we're just going to keep going as we get more and more increasing there. For number 9, we're trying to graph the derivative of this semicircle. So with semicircles, at the edges here, we have an infinitely steep slope. That's essentially a vertical tangent right there. So that's going to give us a vertical asymptote on the derivative, which is infinitely steep there. Same thing over here on the right side. We have a smooth turnaround up here on the y-axis. So at the origin, we're going to have an x-intercept for the derivative. Prior to that, in this interval, we have a positive derivative because the function's going up, and after that a negative derivative because our function's going down. So we have to start above the x-axis for the derivative. We have to follow this asymptote right here, and then we're going down, going through this x-intercept, and now we're going into negative land following this other asymptote. For number 10, we're trying to figure out the derivative for this function, which looks kind of like the cube root function. So first off, we have a vertical tangent here on the y-axis, so that's going to give us an infinitely steep slope. So we'll put an asymptote there for the derivative. Next, on the far left here, we're approaching or pretty darn close to 0. So we're going to have to start close to the x-axis, and we are increasing on the original function, so the derivative then is positive there. Over here, we're still increasing, just at a slower rate. So still a positive derivative, and we're approaching 0 again for the slope. So graphing this thing, we're going to be above the x-axis for the entire time with the derivative. The slope is never negative. We're going to be pretty close to 0 here. We're approaching this asymptote, and then we have to be still positive approaching the asymptote from this other direction and approaching the x-axis on this other side here. So something like this would model that graph in terms of being a derivative. For number 11, we're sketching the derivative of this graph. We've got a cusp here on the y-axis, so that's going to give us a vertical asymptote for our derivative because we're getting infinitely steep at that cusp. Closer here to the left side, our slope is approaching 0, and then we have a positive slope because we're going up, negative derivative, negative slope on the other side as we're going down, and we're getting pretty close to 0 as we move to the far right. So we have to start close to 0 in positive land for the derivative. So that would be somewhere around here. We're going to approach that asymptote as we move to the right. And then over here, well, now we're in negative land. We've got to hug the asymptote down here. So we're starting down here and approaching the x-axis as our slope gets closer and closer to 0. For number 12, we're given the graph of f up here. And we want to pick out which of these could be the graph of f prime, the derivative of f. So this is a process of elimination all the way. I mean, I guess you could graph it up here and then match it, but it's easier just to cross things off. Easiest thing to pick out is that we have two smooth turnarounds here, which means we're going to have two x-intercepts for the derivative graph. Well, which graphs do not meet that criteria? Graph C has 3, that's too many. Graph E doesn't have any x-intercepts. So because our graph needs to have 2 zeros for the x-intercepts for the derivative, C and E are no good. Another thing we can quickly eliminate, choice A has an x-intercept at 0, but the original graph does not have a smooth turnaround or a slope of 0. So that means choice A has a 0 slope in the wrong place, so we can eliminate that. So it's down to B and D. Now the big difference between B and D is that B starts above the x-axis, we're starting with a positive derivative, a positive slope, whereas D starts with a negative slope for the original graph. Since the original graph here has a positive slope to start, that means it has to be choice B, where the derivative is above the x-axis in the beginning. So choice B. For 13, we're given the graph of f, and we want to know for which value of x out of these 5 interval values here is f prime of x positive and increasing. So for this, I'm just going to set it up kind of number line style. So we've got A, B, C, D, and E. And I'll just go through each of these and we'll take a look at what f prime has to be doing based on what the original graph is doing. So at A, the original graph is decreasing, so we have a negative derivative there. So that already eliminates choice A. At B, we have a cusp on the original. That means the derivative is undefined. For C, we're definitely increasing the original function, so we have a positive slope there, so that's good. However, if you notice here, we are increasing, but at a decreasing rate. We're going up, but the rate at which we're going up is slowing down as we get closer to this smooth turnaround. So that means the derivative is actually decreasing, even though it still has a positive value up here. Now at D, the original function is decreasing, so we have a negative derivative, no good. At E, we have a positive slope, so positive derivative, and you'll notice that this slope is getting steeper and steeper and steeper as we go, so that means the derivative is also getting more and more positive. So choice E is the only place where our derivative is both positive and increasing, and that is our answer. For number 14, we're given this even function and asked which of the following statements is false. Definitely the toughest part of this problem is figuring out what they're actually saying here. So for part A, we're basically saying f of 0 minus f of 0 equals 0. This is a continuous function, so the limit of f as x approaches 0 and f of 0 itself are going to be one and the same thing on a continuous function. Well, is f of 0 minus itself going to be 0? Of course. Anything minus itself is 0. All right, moving on to the next one, because that one was true. So for B, D, and E, if you look at these, they all are kind of similar. This is actually the Leibniz definition of a derivative, f of x minus f of a over x minus a as x approaches a. They're all in this form. So they're basically, B, D, and E are all saying the slope of the function at whatever this x value is this y value, or this slope value. So for B, they're saying that the slope at 0 is 0. Well, taking a look at 0, we have a corner there. That is false then. The slope is undefined at 0, not 0. So B is probably our answer, but let's just take a look at the other ones now. So for C, this is just kind of a weird statement. We're saying f of x minus f of negative x, so like f of 3 minus f of negative 3. Now notice that since this is an even function, f of x and f of negative x are always going to give you the same y value. So when you subtract them, you're always going to get 0 in this numerator. All that's really changing then is this denominator, which is getting closer and closer to 0. But since this numerator is always 0, I think it's a safe bet to say that we're at least approaching 0 as we get closer to here. Since it's a limit, we don't actually have to reach there and get the indeterminate form. So moving on to D now, they're saying here the slope at 2 is 1. So looking at the slope at 2 here, this is a slope of 1 right here. We're going up 1 over 1. And then choice E, they're saying the slope at 3 does not exist. Since we have a corner at 3, that is a true statement. The slope is undefined there. So then choice B is the best answer. For number 15, we're given the graph of f of x on the interval of 0 to 4 up here, and we want to know which of the following could be the graph of f prime. So I'm going to do just a little bit of derivative analysis here. So we've got f down here and f prime up here. So here's 0 on the x values and 4. Now between 0 and some place in the middle here, our function is decreasing and then increasing after that. In terms of the derivatives, if you look at this, the original graph starts out pretty close to 0, if not exactly 0, so relatively 0. Then after we go through this decreasing interval where the derivative is negative, we get to this smooth turnaround where the derivative is going to be 0. Then the function's increasing, so the derivative is positive. And then we're getting pretty close to 0 for the slope up here. So let's see if we can find a graph that models this f prime behavior. So A and B can both be eliminated pretty quickly because you'll notice that these derivative graphs are never negative, whereas we know we're going negative for at least part of our derivative. So now we're down to C, D, and E. Let's see now. C is not a very good choice either because we know the derivative has to start pretty close to 0, and C starts nowhere near 0. So now it's down to D and E. E can be eliminated because you'll notice here that we only have one x-intercept between 0 and 4, whereas D has two x-intercepts for the derivative. So at the end of the day then, choice D is the only one we can't eliminate.